visiting all the nodes in a tree is called tree traversal technique. So unlike this nonlinear data structures, that is only logical traverse will be there in linear data structure like arrays, linked list, queues, and stacks. You can go logically in that. That we will discuss later when the topics comes. So here we will visit all the nodes one by one. You can define in different way also the process of visiting the nodes or the process of accessing the nodes in each node in a tree that exactly once. మళ్ళీ విజిట్ చేయకుండా ఒక్కసారి ప్రతి నోడ్ని విజిట్ చేయాలి. The process of visiting the each node in a tree exactly once in a particular order is called a tree traversal technique. So what is the need of this tree traversal technique? This tree traversal technique helps us to visit all the nodes in a tree because the tree is non-linear, means the nodes will be there in different format and different places nodes will be there. And how will you visit multiple nodes using particular order? So this one, there are tree traversal techniques. Uh, we have seen related to something in the graph, no? We have discussed in the graphs, there are two techniques are there to visit each and every node to find out the minimum spanning tree. To find out the spanning tree. How can you generate or obtain a spanning tree from the given graph? Okay. Tree traversal techniques are basically two types. One is depth first search, DFS. And other is breadth first search. This is called BFS. Again, in this DFS, we have three types. Pre-order, in order, post order. So we will, in detail, we will discuss about a particular DFS and how this DFS will work, DFS algorithm, how this BFS algorithm will work. That we will come to know when we are going to discuss about the topic called graphs. And this one, in DFS, depth first search, we have three types of tree traversal techniques. One is pre-order, another is in-order, and the last one is post-order. So in this, what is the last one in these three techniques?
Post order.
Yeah, exactly. You have to remember this order. Pre-order is the first, in-order is the middle, and post-order is the last. So we will discuss about, there may be a question, what is a tree traversal technique? And explain this tree traversal technique using in-order, pre-order, and post-order. They may give you about a list of nodes or elements to construct a BST. You have to construct a BST. Then you have to write about orders. What is the order of pre-order? What is the order of in-order? What is the order of post-order of the given tree elements? So we will see this how this pre-order technique will work, pre-order algorithm, and how this in-order will work, and how this. Okay. This first one. pre-order tree traversal technique. Please, madam, mute. Pre-order tree traversal technique. Okay, I'll take one example from our previously discussed elements, and we will implement this one. Just a few minutes. Okay, friends. Just note down few elements here. If you take this one, elements are like 50, 15, 62, 5, 20, 58, 91, 3, 8, 37, 60, 24. You consider these elements. With these elements, you have to construct the BST, and you can take one more list of elements also. This we can practice it later. 43, 10, 79, 90, 12, 54, 11, 9, 50. Okay. There are two examples, two different types of elements are there. You suggest me whatever the set of elements you want to take to implement this pre-order.
Sir, can you take the 4310 second example?
Okay,
79.
fine, let it. Okay, how this pre-order will work? Pre-order.
There is not ascending order.
Now, first root will come, then left subtree, then right subtree. In the left subtree, root you have to take first, then left node you have to take, and right node you have to take. So you have to remember that P means first or before. Root will come. In pre-order, root will be the first. In in-order, root will be the middle. In post-order, root will be the last. There are only three nodes: root node, left node, right node. In the pre-order, root will come first, then left, right. In-order, root will come in the middle, and before that left will come, and after that right will come. In post-order, root will come in the last. So that's why we have to take these examples like 43. Just let me construct a BST using this one. What is the first element? 43
43.
is the root. The first element. No? Next, where 10 has to go?
10, 10.
10.
10.
10, no, where it has to go?
Left.
Left.
Yes, sir.
Yeah, 10. Next, 79.
Right, right. Right, sir.
Right. Next, 90.
90 left
Right
side.
to 79.
Next, 12.
12 is right to 10.
Left side.
Left.
54.
54 is
Left side.
it's a left to 79.
Next, 11.
11 is left to
10.
left to 12.
12, sorry.
9.
10.
9 is left
Right
to
side.
11.
Left to 11. Left to
50.
10.
Left to 10 also.
50, 50.
54.
50 comes to
Right.
left to 54.
Yeah. This is the BST at the final step. If you construct step by step, this will be the last step of the BST, complete BST. So we have to write the pre-order for this one. Pre-order. Just you have to specify which element will come first and which element will come in the last. Like, so can you suggest me what to take here? So we are following pre-order, no? If it is pre-order, then root will come first. What is the root? Root in this tree.
43.
3.
43.
Yes, 43. Next, left we have to go. Root
10,
is
sir.
over.
10.
Yeah, this is complete. 10 we have to. Left subtree. This is left, in left subtree, we have to take root again.
10.
Next. Again,
9.
9.
9. Next.
12.
Root is
12.
over, left is over. Next again, right
Yes, sir.
subtree. In the right subtree, root has to first.
12.
12.
Level.
Next.
11.
It is not level, it is 11.
11.
11.
Next. Left subtree is over.
Yes.
Right, sir.
Yeah, again we have to go to the, see, first we have taken root,
43.
then left
43.
subtree is over. Then we have to go to the right side. In right
Yes.
side, root has to take first. 79. Then root is over. This root is over. Next we have to go to left. Root complete. Next left.
54.
Left subtree.
54.
54. That is
50.
root.
50.
And anything is there left to 54. You have to 50 is there. Anything is
50.
right to 54. Nothing is there.
No. Yes.
So left subtree is over. Here.
No.
Again we have to go to the right one. This is 90.
90.
This is the order, pre-order of the given graph.
Yes, sir.
Understood?
Yes, sir.
Yes, sir.
Shall we start with in order? In order means root will be in the, can I, just a minute. Is it okay for you?
Yes, sir.
Yeah.
Yes, sir.
In order we will see. In order means left, root will be in the middle, friends. Root,
Right.
right. So let me know. First we have to visit the left subtree. In the left subtree, we have to take which one? Left. We came to
10.
left, no? In that, we have to see any trees are there. Yes. 10.
10, sir.
10, 9. This one
9.
subtree is there.
9.
In that subtree, we have to take again left one. What is the left one here?
9.
10, sir. 9.
9. No, we came to the left side, no? In the left
Okay.
side again, we have to see left.
Okay, sir.
In left side, 10 is there, root.
10.
Yes, sir.
Again, anything is there at left. 9 is there.
Okay.
You have to write that one. Any
9.
other things to the 9? No.
No, sir.
Left is complete. Again, we have to go to the root. What is the root here?
10.
10.
10. So left is over, root is over. Again, we have to go to the right side.
12.
In the right
12
side,
and
again, we
11.
have to visit the left one.
11.
11. Next. Nothing is there. We have to write the root. So
Yes, sir.
to the 12, nothing is there at right. So this left subtree is over here. So left is completed. This is filled up. Next root. What is the root here? 43.
43.
43. Next, right subtree. Left is over, root is over, and right subtree. In the right subtree, again we have to see the left.
79.
No. First we'll go to
54.
50.
54, sir.
No, left.
50,
Sorry,
50,
please. Let me. In the right subtree, some tree is there. 79 is the root, and left subtree is there, right subtree is there.
Yes, sir.
Again, we have to go to the left side. 54 is there. Does it have any left? 54.
Yes, having left
Yes.
50.
Yes, sir.
50 we have to write. Nothing is there to the 50. Again, we will write the root. Root of 50, 54. Next, nothing is there at the left side of 79. Now we will write the root.
90.
Left is over, root is over, and again we will write a right one.
90.
What you can observe, the
Ascending
result
to
of
descending order. Ascending to
order.
descending order.
Let me tell now. The result of in-order traversal is ascending order of the elements. Next one, post order.
Post.
Post order means the root will be the last. This is left, right, root. So may I know? So first we have to take the left subtree. In the left subtree, we came to the left subtree. In the left subtree, some root is there here, 10. For that again left is there. That you have to write 9. So this left is over. Again you have to go to the right one. 12 is there. To the 12 anything is there, right?
No,
No, sir.
no.
So sorry, for 12 we have to write the left one. 11. Then right nothing is there to the 12. 12 will come. So left is over. Left elements. And right element is also over. Next you have to write the root. So this, see this subtree 10, 9, 12, 11. No? First we have taken
Yes, sir.
left one. Again the right one, right elements. This one. For this again left is there. This one will write. Then 12 will write. Again we'll go back to the root. So this left subtree is over. Again we have to go to the right subtree. In the right subtree, again we have to go to the left one. Here it is there. 54. Again it is having any left? Yes, we will go 50. 50 is over. So the 54, anything is right? No. We will write the root 54. This left subtree is over. Again we will go to the right 90. Next 79 will come. This is the post order. So you can note it down the order if you want. This one. And if it is possible for you, I just want you to construct a BST within minutes. And if
Root
you
is
ready,
there, sir.
sorry, madam,
Finally, root is written.
Root
Sir.
is
sorry,
Post order lo root.
43 not sir.
I'm
Sir,
not getting. One person, please. One person. No. 10 is
After
49 actually. Sorry, 43. We missed.
43, sir.
Yeah, 43 we missed. Thank you. Have you understood?
yes, sir.
Yes, sir.
So
Yes, sir.
you may get a question like with some elements, they may ask, construct a BST or binary tree. If it is BST, and they may ask you to write the elements in order, pre-order and post-order traversal. Got it?
Yes, sir.
Hmm. Now we will discuss about which one you want me to discuss. Let me stacks, queues, trees or AVL trees or anything, whatever you like.
graphs చెప్పండి సార్.
Graphs. Why not AVL tree?
Sir, explain AVL tree, sir.
Graphs, I think we have covered in the class.
No, sir.
Graphs, I have taken class.
It's covered, sir.
Who is saying no? I think you are not there in that class. Is it?
Yes, sir. Sorry.
Okay. We will see AVL trees then. AVL trees. Uh, Before entering into AVL tree, I just want you to know, let me know the construction of this BST with the following elements, like 15, 6, 3, 2, 9, 4, and 1. Can you tell me the BST?
15.
No, I just want you to how this BST will look like. With these elements, can you tell me how to construct the BST?
Yeah, we can construct, sir.
Yeah, please.
15, let us take the main element.
Greater
Uh,
than left side,
Root
sir.
of, and left of 15, it
Sorry,
will be root of 15.
I'm not getting friends.
So 15 to be considered as a top element first.
Okay, 1 minute, I'll construct. Yeah,
Yeah.
let me know this one. Yeah, 15 will be the
15, left of 15 to be 6.
1 minute, madam. Yeah, 15 will be there. Next,
Left of
6.
15 is 6. Again,
Again,
left of 6 is 3.
again.
Left of 3 is 2.
Hmm.
Then it is coming to left. No, I mean to say 9, right? Right of 6 is 9. Yes. Again, 3 right is 4. And 2 left is 1.
Is it a BST?
Yes, sir.
Yes,
Yes, it
it
is a
is.
BST, sir.
It is.
Absolutely.
It is following the elements, the
BST.
order of BST only. Then there is some problem. So the BST is not having balance of height. Balance of height. If the elements are more, it is going like there is a tree called skewed tree. Right skewed tree.
It is left skew tree.
Yes, exactly. It is left skew tree. All the elements are there to the left side of the root only.
Yes, sir.
So to maintain the balance factor, to maintain some balance, that means to organize the elements in an efficient way in order to reduce the searching time and to store the elements in the proper order with a less span of time. To save the time and to save the, especially only to save the time only, the balancing factor will be there in AVL trees. So if you want to search for one in this tree, we have to go through this 15, 6, 9, 3, 4, 2, 1. So one by one, we have to search. So to maintain this balance factor, there is no balance. This is in the AVL tree, it is a self-balancing binary search tree. AVL tree also a binary search tree, but it is having a balancing factor. Each node maintains extra information is called balancing factor. Please mute. In AVL tree, what do you mean by an AVL tree? AVL tree is a
Balancing, self-balancing tree.
yes, a self-balanced binary search tree. The name of AVL tree is from the inventors George Adelson, Welsky, and Landis. Their name. So AVL tree is a self-balancing binary search tree. Write it on the screen. AVL tree. It is a self-balancing BST with each node of the tree maintains extra information called balancing factor. Simply, you can define it is a self-balance binary search tree. And the balancing factor can be done at any nodes based on the there is a property or a factor, important factor of this AVL tree, that is every node, the balancing factor of every node should be in the range of -1 to +1. Will you remember how to identify the balancing factor? So the property of binary AVL tree. Can I erase this one?
Yes, sir.
Yes, sir.
AVL tree. Every node should maintain the balance factor. Okay, there is a formula for that. Balancing factor of a node is equals to height of left subtree minus height of right subtree. This is the formula. And balancing factor of a node should be within the range -1, 0, 1. This is what. Will you note it down?
Yes, sir.
This is important one. If you've done once, then I'll move forward.
Finish, sir.
Completed?
Yes,
Done,
sir.
sir.
Yeah. I remember this one. So what is the maximum value of balancing factor?
0 plus 1.
No, the maximum value.
1, sir.
1. The minimum value.
-1.
So the balance factor value should be either -1 or 0 or 1. If it is -1 or 0 or 1 means there is no problem. That is a balanced. So that means that will be a node of AVL tree. So this one, we will take some example here. Can you construct a binary search tree? Or else I'll construct something. Can I erase it?
Yes, sir.
Yes, sir.
I'll take some 30. This is 50. This is 60. And this is something like you take 10 and you some other like 12. And this is like 11. You take some other element as 6. So how can you consider the balancing factor here? This is a BST, right? Is it BST or not?
Yes, sir.
Because 30 is there. 30 కంటే ఎక్కువ
Yes, sir.
maximum elements అన్ని 30 కి రైట్ సైడ్ వచ్చాయి, 30 కి లెఫ్ట్ సైడ్ ఉన్నాయని 30 కంటే చిన్నగా ఉన్నాయి. This is a BST. Whether it
Yes,
is
sir.
AVL tree or not, we have to check. So first you take the first node, that is 30. What is the balancing factor? Height of the left
Height of
subtree.
the left side.
What is the height of the left subtree?
1, 2,
Huh?
2. Yes, sir.
Hmm?
3, sir.
How to identify height, friends?
It's connecting nodes.
Please. From the whatever the node you take, from that node to leaf node in the longest path. See, you can see there are two. For this node, no, this node we have to consider. This way is there. From this way is there. From this way is there. What is the longest path? This one. 30 to 10, 10 to 12, 12 to 11 is the longest path, right? The
Yes,
left
sir.
subtree I am telling.
Yes, sir.
See, if you take what is the balancing factor? Height of left subtree minus height of right subtree, right? What is the height of left subtree? Longest path ఏముంది? 1, 2,
2, 3.
3. So height is 3 here, right?
Yes.
Height of left subtree is 3 minus height
Yes,
of right
sir.
subtree
2.
2. So 3 minus 2. What is the value?
1.
So this is the balancing factor. Balancing factor of 30. How much it is?
1, sir.
1.
So is it a node of AVL tree?
Yes, sir.
Correct, sir.
Yes. To become a tree as a AVL tree, every node should follow the balancing factor. So every node value, balancing factor value should be either -1, 0 or 1. You take this one, 10. Does it have any left subtree? 50? Sorry, you take 50. Does it have any left subtree?
No.
No means 0. Right? No, 50 గురించి డిస్కస్ చేస్తున్నాము. 50 కి
Yes,
లెఫ్ట్
got it,
సబ్ట్రీ
sir.
ఏం లేవు. 0. రైట్ సబ్ట్రీ
We have 1
1. So 0 minus 1 is -1.
minus.
Its value is -1. You take 60. It doesn't have any left subtree. It does not have any right subtree. Its value
0,
is 0. 0. You take 10. Does it have any left subtree?
1.
1 is there. For 10, it is 1 minus right subtree. Height
Right is 2
2. So value is -1.
minus 1.
Next, take 6. Left side ఏం లేవు, right side ఏం లేవు. Means left
0,
side 0,
0.
right side 0. 0. You take 12. Left side is 1.
1,
Right side is
0.
0. 1 minus 0, 1. And you take 11. Left is nothing, right is nothing. 0
0.
minus 0, 0. So if you take each and every node of this tree, this BST, we have constructed a BST. We don't know whether it is AVL tree or not. For that, we have to check whether each node should have the balancing factor, the value in the range of -1 to 1. So you take the first node, each and every node in this BST are following the AVL tree property, balancing factor. So if you take any node, its value either 0 or 1 -1. అవి కాకుండా -2 కానీ 2 కానీ 3 కానీ 4 కానీ ఏమైనా ఉన్నాయా?
No, sir.
No. So every node in this tree is satisfying the balancing factor criteria. Criteria of AVL tree. So it is an AVL tree. Do you agree?
Agree, sir.
Yeah, this one, this is an AVL tree. Now, there are some, if it is not an AVL tree, then what should we do? If it is not what is the need of AVL tree to maintain the height balanced? Example, if you take one small example, can I erase it?
Yes, sir.
Yeah.
Yes, sir.
You take small example, BST. Take the elements like 15, 10, 9. Yeah, we'll take only these three. You take the elements, construct a BST with this, 10 will come, 15 will come, 10 will come, and 9 will come, right? Am I correct? Construct
Yeah,
the
sir.
BST.
Yes, sir.
Yeah.
Yes, sir.
This is the root here. So you can check whether this is a BST for sure, and you can check whether it is AVL tree or not. What is the balancing factor of 15 here? How many?
Sir, it is 2.
What
2,
is the
sir.
Sir. Two, sir.
No. Yeah, 2 minus 0.
2 minus 0.
2. So the balancing factor is 2. The balancing factor of 10 is 1 minus 0. This is
1
1.
minus 0.
And balancing factor of 9 is 0. So to become a tree, a BST to become become an AVL tree, every node should follow the balancing factor criteria. But here 9 and 10 are following the AVL tree criteria, but not 15. To make this one in an AVL tree, we should do some operations. Those operations will be called as rotations in AVL tree. There are various rotations will be there. So what is happening here? See, the rotations can be done only on 3 nodes only. Rotations will be done. Using rotations, we can convert the BST into AVL tree. So there are some operations on AVL trees. Those operations are called rotations of subtrees. So the rotations are called left rotation and right rotation, left right and right left. Left rotation, right rotation, left right rotation, right left, rotation. These rotations can be done in order to convert a BST into an AVL tree. So what is the possibility here to rotate? Hmm? Any idea? So that the rotation, after rotation, it should not violate the BST property. Rotate cheste
AVL tree properties, right?
no. that should follow the AVL tree property and BST property.
Okay.
See, we will rotate to convert it into AVL tree only. Once we convert the AVL tree by rotating, that rotated tree, which is AVL, should not violate the property of BST. Any idea?
Sir, 15 comes under right to the
Yeah, how? What we call this one?
That
right
is called right rotation.
Huh?
Right rotation.
Is it right rotation?
We are moving to right only.
Left, sir.
Left, sir.
Left or right? How
Left.
it is left and how it is right?
right only. Sir.
Right rotation only, sir, because to 15 we are moving to right.
Then only 10 will take the root, sir.
10. Right of 10 we are moving.
Right of 10. See, this is called which direction?
Right.
It's
Right rotation. This is called
Left.
left. Just remember this. So, these rotations can be done only on 3 nodes. Only 3 nodes. So, what are the things? What should we do? So, here, this is there at left node and again left node. So,
Yes,
if
sir.
it's having left and left, and you do right rotation. Left rotation or nothing but right rotation. What should we do? In this 10 will go up and 15 will come down. So this is called right rotation only. See, we are moving 10 to right direction. 10 will come here. 9 will be there here only. And again, we are moving 15 to this way.
Okay.
Does it violating the property of BST?
No, sir.
10 is there. దానికి maximum ఉన్నాయి రైట్ సైడ్ వస్తాయి. దానికంటే స్మాలర్ ఉన్నాయి లెఫ్ట్ సైడ్ వస్తాయి. And if you take this AVL tree, balancing factor, what is the balancing factor of 10 here? Left subtree is 1 and right subtree is 1. This is 0.
1 minus 1.
Yeah, 0. This is also 0. This is also 0. So the nodes, balancing factor of each node value should be either -1 or 0 or 1.
Plus 1.
Yeah, that's what. So it is satisfying the AVL tree property. So you have to note that an AVL tree is a BST with each node is having a balancing factor. Each node will have information about balancing factor. The balancing factor value of each node should be in the range of -1 to 1. So every node should satisfy the balancing factor criteria. Then only it will be called as an AVL tree. AVL tree is a height balanced tree. This is what. And if that the BST is not an AVL tree, it not maintaining the balancing criteria, then to convert a BST into an AVL tree, we will do various operations. Those operations will be called as rotations. Those rotations are left rotation, right rotation, left-right rotation, and right-left rotation. These rotations. This first you should know the property. Balancing factor is equals to height of left subtree minus height of right subtree. What is the height? What is the height of a particular node? The height of the particular node is
Longest path, which is
the number of edges in the longest path. ఆ నోడ్ నుంచి ఉన్న paths లో లాంగెస్ట్ పాత్ లో ఉన్న నెంబర్ ఆఫ్ ఎడ్జెస్ ఉన్నట్టు దట్ ఈస్ కాల్డ్ height. So you should remember all this height and these rotations. And in detail, tomorrow we will discuss about this one, these complete rotations. We'll focus only on rotations. Once these rotations are done, then we will go with some other important topics. Then only we will come back to the other trees. How these rotations will work. And we will try with more elements. I think if you start once, I think they may close the class session. Only 2 minutes are left. Okay, friends.
Thank you, sir.
Okay, sir. Thank you, sir.
Just practice
Thank
the
you, sir.
BST in order, pre-order, post-order. And this AVL tree is also important one. And the graph.
Okay, sir.
And I'll take the class on 12th and 13th also.
Okay, sir.
Okay, sir.
After requesting, after getting permission from concerned department. Because we missed 2
Okay,
classes,
sir.
no? I'll request them. If they give permission, then I'll take the class.
Okay, sir.
Okay, sir.
Yeah, fine. Thank you.
Thank you,
Thank
sir.
you, sir.
Sir.